Hello students, welcome back to JCE Connect. So we'll continue with the problems on curved veins. Let us take the next problem. A jet of water of 60 millimeter diameter strikes a curved vein at its center with a velocity of 18 meter per second. The curved vein is moving with a velocity of 6 meter per second in the direction of the jet. The jet is deflected through an angle of 165 degree. Assuming the plate to be smooth, find the thrust on the plate in the direction of jet. So here thrust means the force on the plate in the direction of jet, then the power of the jet and efficiency of the jet. So let us take this example as a assignment homework, and a similar problem we have solved in previous lecture. So please refer that one, and in a similar way you solve this problem. Let us take this problem as a assignment. Take a next problem. So in this problem, it is been given here: a jet of water from a nozzle is deflected through an angle of 60 degree. A jet of water from a nozzle is deflected through 60 degree from its original direction by a curved plate which enters tangentially without shock with a velocity of 30 meter per second, and leaves with a mean velocity of 25 meter per second if the discharge from the nozzle is 0.8 kg per second. Calculate the magnitude and direction of the resultant force on the vane if the vane is stationary. Okay, so here first write the given data. So what is been given here: the velocity of the jet at inlet, that is V1 30 meter per second, and the velocity at outlet V2 is 25 meter per second. Then the mass per second, that is directly the mass per second is given, that is rho AV. This is rho AV, which is been given directly as a 0.8 kg per second. The force in the direction of jet, the formula we know, Fx is mass per second into initial velocity minus final velocity, that is V1x minus V2x. First, with the given data, you draw the figure. So this is the curved vein given like this, and here what is being given, see, from the nozzle, jet of water from the nozzle is deflected through an angle of 60 degree. So the angle of deflection, that is jet is deflected through an angle of 60 degree from its original direction, means this is the direction of the jet which is entering tangentially into the passage of the curved vein. If this is a horizontal, then the deflection angle is acute angle, then that is a 60 degree. So the moment it strikes, it will deflect like this, then by making an angle of 60 degree here. So it is given as an angle of deflection 60 degree. So this velocity it is entering, enters, glides over the surface like this, and it exits like this. And the exit velocity is also given, that is 25 meter per second. Here inlet velocity is 30 meter per second. With this velocity it is entering, but exit velocity is 25 meter per second. Hence there will be some losses here. Because of that losses, the outlet velocity what we are getting here is 25 meter per second. And with this velocity it is exiting, but by making an angle of 60, because this is the deflection angle given. So water will be striking in this way. It enters tangentially, then it glides over the surface like this, and it exits by making an angle of 60. That is the deflection angle is given here. Then when the velocity is given here, the exit velocity, but it is making an angle of 60 degree with horizontal. Let us resolve this velocity into two components, one in a vertical direction and one in the horizontal direction. Vertical component becomes 25 sin 60, and the horizontal component becomes 25 cos 60. And the vane is fixed. It is given a fixed vane, that is a stationary curved plate. Here the jet of water from a nozzle is deflected through an angle of 60 degree from its original direction. Hence we have drawn the vane like this. This is the original direction of the jet. The jet is striking here. This is the, can take it is a jet like this. The jet is striking the vane and at one of the tip and entering tangentially. This becomes tangentially and deflects. This is the original direction of the jet. With from this direction it is deflecting through an angle of 60 degree. Okay. So once you draw the figure, then it is very easy to calculate the force. So everything we have to refer from the figure and we have to substitute in the formula. So here mass per second, Fx will be mass per second, in that is v1x minus v2x. What is the v1 here? V1 is this v1 with what velocity the jet is entering into the passage of vane. So v1x will be v1 is 30 meter per second and v2x is again in the direction of jet only we have to take. So this is the direction of the jet. So v1 is the initial velocity and v2 is the final velocity, but the component of this v2 to be taken, that is 25 cos 60, that will be v2, 25 cos 60. So we get 12.5 meter per second. Then one substitute in the above equation directly. The mass per second is given. This is a 0.8. This is a mass per second, that is 0.8 kg per second. Directly this mass per second is directly given. Substitute this one, then substitute initial velocity minus final velocity, we get the 14 Newton. Similarly, force normal to the jet, Fy mass per second, v1y minus v2y, again v1y. Initially in y direction there is no velocity here. Okay, there is no, this is y and this is x, so there is no velocity in y direction, hence velocity in y direction will be 0 and velocity in y direction at exit will be 25 sin 60. We get 21.65 Newton. Then calculate Fy, we get minus 17.32. That minus sign indicates the jet will be acting vertically downward. Then the resultant r equal to root of fx square plus fy square, then resultant will be 22.27 Newton. Okay, then calculate the direction of the resultant. Then the direction of the resultant, there is angle made by the resultant force with x-axis. Angle made by the resultant with x-axis, that is tan alpha is Fy by Fx, then minus 17.32 divided by 14, we get tan alpha is 1 minus 1.237. Negative sign means the angle alpha is in the clockwise direction with x-axis. So we get alpha is 51 degree 2.86 second. That means the alpha will be in clockwise direction. So generally we measure angle in an anti-clockwise direction, but in this case the angle to be measured in a clockwise direction, that's why it is we are getting here a negative. Then fx is a positive, fx we have got as a positive and fy is a negative. We have to draw the negative y direction, and fx we have to draw in a positive x direction. Then this is the resultant. Okay, finally we have to draw this one. Then let us take one more example. Next, a stationary vane having an inlet angle of 0 degree and an outlet angle of 25 degree receives a water at a velocity of 50 meter per second. Determine the components of a force acting on it in the direction of the jet, velocity and normal to it. Also find the resultant force in magnitude and direction per kg of flow. This is very, very important, per kg of flow. And in the second part, what is been given here, if the vane stated above is moving with a velocity of 20 meter per second in the direction of the jet, calculate the force components in the direction of the vane velocity, and across it. Also the resultant force in magnitude and direction, calculate the work done and power developed per kg of flow. So here in this problem there are two cases. The first case is a stationary case and the second case is a moving case. And let us write first the given datas in this problem. What are the datas given in this problem? First take the stationary vane. So the given datas here, the inlet angle of the vane is given 0 degree. With this angle the jet will be entering tangentially. Outlet angle of the vane is 25 degree. Then the velocity of the jet is 50 meter per second. Then draw this diagram. This is the diagram you have to draw like this. So draw this vane, and this is fixed one. The vane is fixed here, and this is the velocity of the jet, but the angle here is 0 angle. Theta here is 0 inlet angle. So it enters and glides over the surface. Then it exits by making an angle of 25 degree here with the same velocity. And when we resolve this one, we get vertical component as well as the horizontal component, v cos 25 and v sin 25 like this. So this is a stationary vane. So for this one, let us calculate fx. Fx will be, and this is a mass per second. We know mass per second into initial velocity minus final velocity. We know this formula, and mass per second is given. So we have to calculate per kg of flow. So we have to calculate 1 kg per second for flow. So directly the mass flow, that is mass flow rate is given, mass per second is given here in this problem. Substitute directly 1, then v1x minus v2x. v1x is given and v2x is equal to minus v cos 25. It is in the opposite direction of the jet we are having here. The jet is exiting opposite direction of the inlet jet, incoming jet. This jet is going out of the incoming jet. This is the incoming direction, this is the outgoing direction. Then we get finally 95.315 fx. Then similarly calculate fy. So we get a fy as here. Similarly, the force exerted by the jet in the direction perpendicular to the direction of the jet per kg of flow. Then fy will be 1 into v1y minus v2y, where v1y is 0 and v2y is v sin 25, 50 sin 25, 21.13 we get. Then fy is 1 into 0 minus this one, we get this one. Then the negative sign indicates that fy is acting in the downward direction. Then finally the resultant force we have to calculate, that is r equal to root of fx square plus fy square. Then substitute the values of fx and fy, we get the resultant force as 97. Then the angle made by this resultant with horizontal, that is with x-axis, that is tan alpha is fy by fx. Then we get the angle as a negative. That negative sign indicates the angle to be measured in a clockwise direction like this, and this indicates the resultant force. Then fx we got a positive in positive x direction, in a positive x direction we got a fx, and in negative y direction we got a fy. Then the resultant of these two, that the angle to be measured in a clockwise direction, we get this as the resultant force. Then in that same problem, what is the next case? Is a moving vane case. So velocity of the vane u is given. So previous case was fixed case. Now the same velocity of the jet which is striking the vane, but the vane is moving with a velocity of 20 meter per second. Then the force exerted by the jet on the moving vane in the direction of jet. So here the same vane to be taken, but it is a moving, this vane is moving with a velocity of 20 meter per second, that is velocity of vane. Then the effective velocity becomes here is v minus u, because both are moving. Then the jet will be entering with a velocity of v minus u. Then it enters like this, then it exits v minus u. Again you have to resolve into two components, one in a vertical and one in a horizontal direction. That is v minus u cos 25 and v minus u sin 25 we get, and the vane is moving in x direction. Okay, so for a moving vane case we have where v1x equal to v minus u, then we get v1x Then v2x will be minus v minus u cos 25 in the like this one, which is in the opposite direction of the incoming jet. We get this one. Then finally calculate fx 1 into, that is 1 is a per kg of flow. We have to take the same, but the case is moving case. Then we get fx like this, and fy you calculate again per kg of flow, v1y minus v2y. v1y is a 0. We don't have any y component here. Then v1y is 0. Sorry, v2y. Sorry, v1y is 0, and v2y will be v minus u sin 25. Then we get this as a 12.67 meter per second. Then finally the fy will be minus 9. Then the resultant force, we calculate the resultant force, root of fx square plus fy square. Substitute the values here, we get 58.57 Newton. Then the angle made by the resultant with x-axis, tan alpha equal to fy by fx. Then we get minus angle, that minus indicates the angle to be measured in clockwise direction. Then we have to draw this one. We have got positive fx and negative fy and resultant force like this, and you have to measure alpha in a clockwise direction. Then the work done per second, this is the work done per second, fx into u, and we know the velocity of plate. This is the work done per second, Newton meter per second. The power developed, the same to be written in terms of watt. So 1.1438 kilowatt the power generation. Okay, I hope you understood these type of problems. So please practice these type of problems. Let us take one more example, so which is a very important example. So in this problem, a 60 millimeter diameter horizontal jet of water, 60 millimeter diameter horizontal jet of water at 10 meter per second, striking tangentially a stationary curved vane, smooth vane, which deflects the jet by 135 degree. Find the force of the jet on the vane and its direction. If the vane is moving at 5 meter per second in the direction of the jet, determine the power transferred and its efficiency. Also, if there are a series of vanes, how will the efficiency change? Okay, this is a problem given here. So here there are three parts given. First part will be the stationary part, second part is a moving part, and the third one they asked, instead of having a single vane, if there are series of vanes, how the efficiency will get changed. So let us write first the given data. The data given here is the diameter of the jet is given 60 millimeter, that is 0.06 meter. Calculate the area of the jet, then pi by 4 d square, we get the area of jet this much. Then velocity of the jet given, then angle of deflection is given, then the velocity of the vane is given. Let us take the first case, the stationary vane. The vane is stationary, so this is the case. So the jet is entering with this velocity, but the angle is not been mentioned here. Let us assume it is entering with an angle of 0 degree. So it is entering tangentially like this. So after entry, then it glides over the surface and exits like this, but the angle of deflection is given as 135 degree with horizontal. Then this angle will be 45 degree, this angle equal to this angle. Then when we resolve this component v, one we get a vertical and one we get a horizontal, that is v cos theta and v sin theta. Then apply impulse momentum principle, fx equal to rho a v, that is mass per second, into initial velocity minus final velocity. Then rho a v, initial velocity is v minus v cos theta, then we get minus v cos theta here. Then we get fx equal to this one. Then substitute all the given data here, we get this much is the force exerting by the jet in x direction for stationary vane. Similarly calculate fy. So this is the fy we get, initial velocity minus final velocity, but initial velocity is 0, final velocity is v sin theta, we get 199.89 Newton. calculate the resultant force, that is root of fx square plus fy square. We get this much is the resultant. Then calculate magnitude of the direction of the resultant, theta equal to tan inverse of minus fy by fx. We get minus angle, that minus indicates the angle to be measured in clockwise direction. So fx, the fx we got positive x direction, fy we got negative y direction, and this is the resultant of fx and fy, and the resultant will be acting at an angle of theta, that is 22.5 degree. Then the next case is given if the vane is moving, if the plate is moving with a velocity of v, u equal to 5 meter per second. So what is the efficiency of the jet, they have asked. Then calculate fx, mass per second, then initial velocity minus final velocity. Then we know for a moving case we have to take the effective velocity as relative velocity, that is v minus u, then into bracket v minus u minus of v minus u cos theta. Then finally we get fx equal to 120.65 Newton. Then work done per second, that is the force into velocity of the plate. Then we have calculated fx, then multiply by the velocity of the plate, we get this much. Then the power in kilowatt, that is 603.25 is a new work done per second. Then the power in kilowatt will be 0.603 kilowatt. Okay. Then finally the efficiency of the jet will be what? Work done per second is the output by input. The work done per second is the output. Input will be the kinetic energy of the jet. Then the kinetic energy of the jet per second, that is half rho a v q. Then when you substitute all the rho a v, we get this much is the power, that is we get a watt. Then the efficiency of the jet, substitute here, then we get the efficiency of the jet as 42.67%. This is for single vane. So what they ask in the problem, if the series of vanes are present, like if the series of vanes are considering, if there are series of vanes like this is the impeller, this is the shaft. If series of vanes are present like this, what could be the change in efficiency, the question. And this efficiency what we have calculated is for single vane present over the impeller. If series of vanes are present, what is the change we get here? If the series of vanes present, the change what we get here, the only change we get is a mass per second. So in previous case, the mass per second is to be taken v minus u rho a v. Here when we consider all the vanes together, the jet will be in touch with the vanes, hence we have to take the rho a v, and v minus u initial velocity minus final velocity. Then finally we get fx this much. Only this is the change. Then v minus u rho a v into bracket v minus u 1 plus cos theta. Then substitute all the values given. Then we get the force in x direction. Then calculate work done per second, again fx into u. Then this much is the work done per second. Then efficiency of jet, output by input, that is work done per second divided by kinetic energy per second. Kinetic energy already calculated. This is the change, that is the work done per second for a series of vanes. Then finally efficiency we got 85.35%. This is compared to the single vane, this efficiency is more. Okay, I hope you understood these kind of problems. So please practice this type of problems and solve it. Okay, thank you.